I'll be presenting my research on accelerated life testing of deep groove ball bearings using contamination failure. My supervisor is Professor Melinda Hodkiewicz. Bearings are everywhere. They are in all rotating equipment, including compressors, turbines, crushers, pumps, motors. Bearings allow the free rotation of moving parts, and although 90% of bearings exceed their expected lifetime, around 0.5% of bearings fail prematurely. And in a market where 10 billion bearings are produced every year, this can have catastrophic results. When bearings fail, especially prematurely, they can have effects on supply chain, downtime, or production. There are ways to predict bearing failure through a method called condition monitoring, which looks at different sensor information and tries to predict when faults occur. To drive my research, I've asked myself the following question. How do you induce failures in bearings in an accelerated and repeatable way using contamination as the method of failure? The reason I've asked myself these questions was I found gaps in the literature. A lot of the research focused on the analysis of the sensor data from damaged bearings, but they often had poor design of experiment, not clearly articulating how they damaged the bearing or what method they used. Often these tests had long durations or simply did not state the time at all, which is important when reproducing the experiment. Thirdly, all the experiments used purpose-built test rigs with a motor attached to a shaft with some bearings on it. And while this is useful in recreating the experiment, it doesn't allow the challenges encompassed with using an industrial piece of equipment such as damping or mounting. Lastly, the tests in the literature tested uncommon failure causes. As you can see here, most of the failure causes for bearings are through contamination or lubrication. However, this was underreported in the literature in the type of tests used. There is a standard for bearing testing using journal bearings. However, this procedure doesn't go into the types of tests to do, rather what type of outputs should be coming out of testing. The goal of this work is to create a method on how to accelerate failure that can be replicated. To do this, I've created two different tests. The first test is a mixed grease test, where two different greases with different mechanical properties, such as different viscosities and a base thickener, are mixed together in a thrust bearing. The second test is a dirt contamination test, where 5 grams of dirt that has been screened to under 70 micrometers in size is mixed with grease and then packed into the thrust bearing. The goal of both of these tests is to accelerate the failure so that we reach the potential failure as quickly as possible. The difference in my research compared to the literature are 4 things. Firstly, there will be a method that will clearly explain exactly what's been done to the bearing and the whole testing process. Secondly, the testing duration will be short, between 1 to 3 hours. Thirdly, a test rig will not be used, rather an industrial piece of equipment, a pump, will be used. And lastly, the method of failure cause, or the failure cause for these tests, will be common to actually what happens to bearings. So this is through contamination and the mixing of greases. This project will be conducted using the UWA pump test rig, which features a Gould's 3196 MTX pump coupled to a 1500 watt motor. This pump has 2 bearings in it. On the left here we can see a radial bearing, and on the right is a thrust bearing. For all of the tests, the thrust bearing lubrication environment will be changed, while the radial bearing will always have the same amount of grease in each test. To validate the results, the temperature of the bearing housing will be monitored both on the thrust and radial side of the bearing housing, and a frequency analysis will be conducted by using a piezoelectric accelerometer mounted to the bearing housing. There are 4 different components in a bearing. There's the balls, inner race, outer race, and cage. When these components move, they move at a relative speed compared to the driving speed of the shaft. And you can look at this relative speed in the frequency spectrum to see if additional impacts or knocks are created. In table 1, you can see the frequencies calculated for the ball, inner race, outer race, and cage, and this will be used in the results section. The mechanical seal is the most critical piece of equipment in the pump, and also the most likely to break in a bearing changeout, which cause some problems down the line. Here we can see the removal of the shaft by the fitter, which has the two bearings on it. Hydraulic press is used to remove the bearings from the shaft, and after this, an eddy current heater is used to press the bearings on the new bearings onto the shaft. Lastly, here we can see the bearings being packed with grease using a syringe to make sure that the same amount of grease is used every time. And lastly, we've got the mechanical seal being installed onto the shaft. The control test was conducted with both bearings in an oil bath as the lubricant. There were some unforeseen delays, which I'll get to a bit after, which is why the control test couldn't be conducted using two grease-packed bearings, but this will be conducted later in the semester. The idea of the oil bath test was to see what temperature did the bearing housing get to and what was the frequency spectrum. Maximum temperature of the bearing housing was 33 degrees over a 3-hour period, and the frequency spectrum showed the driving frequency at 1F, harmonic 2F, and also knocks on the outer and inner race shown by the BPF on BPFI. However, there weren't harmonics of these, and looking at the bearings coming out of the first changeout, both of the bearings were in excellent condition and there were no visible defects. The mixed grease test showed some interesting results. The thrust bearing is packed with two different types of greases, Shell Alvania grease and a thermaline grease, while the radial bearing was packed just with thermaline grease. As you can see in figure 9, the thrust bearing rose in temperature rapidly over the course of a 1-hour period of testing. After 60 minutes, the bearing housing reached a temperature of 48 degrees, at which point testing was ceased, firstly because the bearing was getting very hot, and secondly because the beeswax used for the piezoelectric accelerometer started to melt. The frequency spectrum for the mixed grease test showed some interesting results over the course of that hour. In the high frequency range, after 60 minutes, there were high bands in the 8 kilohertz range. And in the lower frequency response, we saw lots of different knocks on the outer and inner race only. What was interesting is that in this BPFI, we can see how it's changed over time. The amplitude has increased greatly on the inner race. When the bearing was pulled from the shaft, an angle grinder was used to cut up the bearing to see if there were any localized defects on the thrust bearing. Except for some slight discoloration on the outer race, there was no real material defects. However, this was to be expected as the two greases interacted with each other. They actually caused more friction, which is why the temperature rose. There's also evidence that the grease was overpacked, as shown in figure 14, where grease was actually thrown out of the bearing through the rubber shields into the bearing casing. The dirt contamination test was conducted by mixing 5 grams of dirt with thermaline grease, and then packing this into the thrust bearing only. However, when the bearing changeout happened, the mechanical seal chipped. I mentioned earlier, the mechanical seal is the most vulnerable piece in the pump, and it is recommended to replace this piece every time a bearing changeout is done. However, due to the short duration of testing between bearing changeouts, we decided that we would rather replace or repair the components in the mechanical seal. Due to some delays from COVID, there were extensive shipping delays in actually getting parts to Western Australia, which is why this test hasn't been completed. And on top of that, there were delays in KSP with its scheduling, which is why this test has been delayed to June 2020. The most important discussion point is whether or not these tests actually created failure. The mixed grease test did create failure. The bearing got very hot, and when looking at this frequency spectrum compared to the oil bath control test, you see firstly high frequencies in the 8 kilohertz range, and also increased knocking, which we could see the change over time. The dirt contamination test hasn't been conducted yet, but I'm confident that this will achieve an interesting result due to the amount of dirt packed in the bearing. Experimental method is the key deliverable from this project, and the discussion on what went well and what went wrong is really useful. The motor used in this test was only 1500 watts, which is smaller in comparison to what you find on most industrial sites. One of the goals of this test was to simulate a real industrial system, but by having a smaller motor than what you would find on an industrial site, hasn't quite worked out. However, this motor was able to drive a shaft at 1400 RPM and also generated some nice frequency plots. Secondly, the bearings never experienced true run-in period. A run-in period is normally conducted after bearings have been installed to get them accustomed to the environment with the new lubricant conditions. However, this wasn't done and can be considered a vital omission that should be conducted in future tests. There were problems with the bearing changeouts, including receiving the wrong bearings from the pump fitting company, and also problems in recommissioning the pump after bearing changeouts. One problem was that the impeller was rotating the wrong way and actually jammed on the involute case. And another large problem was the chip in the mechanical seal and just the time it took to replace that. The sensor data, while useful and proving in the failure of the bearing, could be done differently. Firstly, the temperature of the actual bearing should be monitored, not just the bearing casing. And secondly, the vibration data should use a mounting method that is independent of temperature, such as a magnet or a piece, such as a stud. Fifth, the usage of dirt for the contamination test was good in the fact that this type of test has not been done before, but it's hard to reproduce these kind of results because the screening and material properties of the dirt are hard to justify. The screening of the particles can be conducted, but there were no available tests for the size of particle to look at the hardness of the soil sample. Lastly, all of the bearing changeouts required a workshop to be present where the pump was, otherwise the pump would have to be stripped and then taken to an external facility, increasing the cost of testing. My research looked at using a pump opposed to a test rig, and there are 3 discussion points from this. Firstly, there is more variability in all of the tests. By using a pump with different bearing changeouts, the system changes from time to time, especially as some seals have to be used again until they can be replaced. The time it took to do a bearing changeout was also a factor in why you would use maybe a pump or a test rig. Because a contractor had to be engaged to do the bearing changeouts, it increased the time to do these jobs. The actual time it took to do the bearing changeout was between 4 to 8 hours. However, there were complications with things like using the mechanical seal, which broke and had to be relapped. Thirdly, the sensors cannot be put into the spots where you'd ideally have them, which you could design if you're building your own test rig. The last discussion point is on the usage of university equipment for testing. Prior to any testing occurring, an electrician was called to determine if the system was safe to use and whether the controls in place were adequate. The electrician found that there were some code violations, especially to AS3000, that had to be rectified. Things including using the wrong type of material, the wrong type of resistors, and the wrong type of IP certification for the controller. These issues had to be rectified using a contractor, and it's a worthy consideration when doing any type of testing on university equipment to make sure that it's actually up to safety standards. Future work includes validating the results in different types of rotating equipment to look at other types of bearing failure in combination, such as shaft misalignment and contamination. Thirdly, it's to look at how time and temperature align over time, and also to take more continuous data and more useful data by getting, for instance, the temperature of the bearing, not the bearing housing, and to look at testing where there isn't a need for someone to be present, so autonomous testing. Lastly, it's to do a bearing run-in period for the bearings on a test rig or prior to installation. Thanks for watching my presentation.